Kia ora everyone. Welcome to the New Zealand Society for Earthquake Engineering webinar series. This is the second seminar in the series, and the seminar is themed on seismic performance of non-structural elements. I would like to welcome you all in this session, and we have got two very well informed and well experienced speakers lined up today. And I am Rajesh Dhakal, a professor of structural engineering at University of Canterbury. I will be convening this session together with my colleague Andrew Baird. So just a bit of few housekeeping information. If you haven't heard about the announcement, there is the national conference annual conference of NZSEE coming up in April 2003. That is scheduled to be on 19 to 21 April. Will be based in Auckland, University of Auckland. And the deadlines for submission of abstract is about a month from now, 28th of October. There are other deadlines also and other information in the website that you can see on the screen there. While we are on this topic, I would like to also introduce you to an international initiative on seismic performance on non-structural elements. So there is an international association, which is acronymed as SPONS, Seismic Performance of Non-Structural Elements. This was established back in 2014 when we gathered in China for an international workshop on this particular topic. This association, it has got a virtual office in that website. You can see www.spons.eu, and there you can find a lot of useful information on anything related to seismic performance of non-structural elements. Those of you who are not aware of it, probably you might want to just browse in and see what sort of information is there. The membership is free. You can either register as an individual member or organizational member. You can see on the right of the screen the committee or the directors there, and you can see three names there from New Zealand. Myself, I'm acting as the president of the association at the moment, and my colleague Tim Sullivan is also a director, and Andrew Baird from Baird, who's my co-convener today, is also a director of the board there. So those of you who are interested, please browse in and see. The most important thing is there is an international workshop on SPONS that is coming up in 5 to 7 December this year at Stanford University, California, in partnership with Applied Technology Council. These are the general information. Once again, I would like to welcome you all to today's webinar, and I would pass on to my co-convener Andrew to introduce himself and to introduce today's topic and speakers. Up to you, Andrew.
Thanks, Rajesh, and hi everyone. So my name's Andrew Baird. I'm a senior associate at Baird, based in our Auckland office up here. Very excited to be hosting this webinar alongside Rajesh today. I think we've got two very good presentations with a really good mixture of where things are at in regards to both research and design of non-structural elements. So I'll introduce both speakers now. They've both got about 20 minutes, which should leave some time for some Q&A at the end. So save your questions to the end. I think we should be able to post your questions within Zoom. So there's a Zoom little Q&A button. So post your questions in there, and I think it's also possible to upvote questions. So use that feature, and then we'll come to those at the end. So I'll just quickly introduce both speakers and let them get on with it. So our first of our two speakers is Jan. So Jan Stanway is a principal structural engineer at WSP, where she's involved in the seismic design of non-structural elements in various new and existing buildings. Jan is also the industry champion for the fit-for-purpose building components of the Building Innovation Partnership. This group's doing some really great things, bridging the gap between research and industry. So Jan's talk today is going to provide an overview of the key issues impacting design, coordination, and installation of non-structural elements. She's also going to discuss the importance of taking a holistic view on the response and function of the building when seeking to improve the performance of non-structural elements. Our second speaker is Dr. Jitendra Bhatta. Jitendra is a seismic restraint engineer at Becca, and he holds a PhD in earthquake engineering from the University of Canterbury. Jitendra's PhD research focused on the development of seismically resilient non-structural elements, in particular precast concrete cladding and internal partition walls. So Jitendra is going to talk about the findings from his research into the detailing for these drift sensitive elements, including a novel low damage detail of a rocking precast cladding panel and internal partition walls that he tested at University of Canterbury. Jitendra's presentation is also going to highlight the importance of taking an integrated approach to non-structural elements. So I think that's quite a common theme that you'll hear from us today, something that I also feel quite passionately about. So that's probably enough from me. So I'll stop sharing my screen and pass on to Jan.
Thanks, Andrew. I will share my screen. Right. So, yeah, my presentation today is on seismic performance of non-structural elements and what have we learned. So I just want to run through very briefly, why is the seismic performance of non-structural elements important? What were the main causes of damage and what are the key issues facing the construction industry that impact the seismic performance of non-structural elements? I want to talk about the impact of the performance of the primary structure on the seismic performance of non-structural elements and what can be done to improve the seismic performance of non-structural elements. So starting out, why is it important to have good seismic performance of non-structural elements? Well, non-structural elements typically contribute to about 80% of the total cost of the building. And we had extensive damage to non-structural elements in the Canterbury earthquakes, Cook Strait earthquake up in Wellington, where the accelerations weren't as high, and the Kaikoura earthquake. And the damage that we observed highlighted the complexity and the duration of the repairs to non-structural elements significantly impacts business interruption. And the costs of damage are twofold. Firstly is the repair and the replacement of non-structural elements. But importantly, business interruption can't be forgotten because in most cases, it was actually a significantly higher cost than the material damage costs where those businesses couldn't go back to their offices immediately, or they had to remove themselves from their offices to actually enable the repair or the replacement to be undertaken. Did I zoom past? Sorry. So what have we learned? That good seismic performance of non-structural elements is important, but it's important not just for our hospitals and post-disaster facilities. It's important for our homes, our apartment buildings, our office buildings, our industrial buildings, and our transportation links. Because what we found was that the ongoing operation of those buildings is essential for the continuation of our economy and the well-being of our communities. Oops, sorry, having trouble. There we go. So what were the main causes of damage and the key issues facing the construction industry? So the main causes of damage was poor overall design and coordination. We saw a lot of places where there was inadequate or lack of seismic restraints for non-structural elements, insufficient clearances between building components to cater for the interaction between components, and incompatibility between the drift of the structural system and the drifts that cause damage to drift-sensitive non-structural elements, your facades, cladding, partitions, your fire systems, your passive fire systems, and your weather tightness. And the Building Industry Partnership did some research back in 2020 and found that there were actually underlying construction industry issues that were causing the poor performance that we'd observed during the earthquakes. And the key issues were found to be procurement, where they found that the procurement methodologies push the risk down the chain to the contracting teams, and that risk is then poorly managed throughout the project lifecycle. We found that there was limitations in knowledge, particularly clients, of what they were going to get if they chose code minimum performance compared with resilient options. We found that poor holistic design and coordination between the design disciplines was occurring from the start of the projects, and that there was poor coordination between subtrades on site, and that combined with installation behaviours that were driven by lowest price conforming tender processes was resulting in poor outcomes. We also found that there's a lack of knowledge and skills and training throughout the industry. And last, but certainly not least, there was a lack of independent QA. So I just want to talk briefly about the performance of the primary structure and its effects on non-structural elements. So from the concept phase, the design of the primary structure should be completed to achieve the drift limits for the required performance of the non-structural elements. So I've just made some notes here on things that should be considered by the structural engineers. They should be thinking about what's in this building. Are there partitions? Are the partitions full height? Do they stop at the ceiling level? Do I have firewall partitions? If I do, is the intent that they run from floor to floor or the underside of the roof? Or is there an intention to have the fire rated ceilings to run just above, fire rated partitions to run just above the ceiling level, and then have a bulkhead with a fire rated seal coming down from the top to create the firewall? In each case, what detailing will be required? What costs will be required? Noting that the damage to partitions can initiate around 0.3% drift. Also to be asking, what's the cladding system? And for that cladding system, what's the drift limit for the initiation of damage to the proposed cladding system? Some work done at the University of Canterbury by Arifin and others in 2020, down in the bottom left-hand corner, was they did some work on a commercial glazing system and found that you can start to lose water tightness at a median drift of 0.35%. When you've got multi-story apartment buildings, you've got often you've got these tiled with membranes and tiled wet area showers with membranes in behind. And that's particularly an issue for drift, where in the corners, the membranes are actually very vulnerable to being torn under drift. So my key point here is that the design of the primary structural system needs to achieve the seismic performance of the non-structural elements. And when it's holistically considered, the most cost-effective overall solution will be found. So what I'm trying to point to there is, let's not design the structural system and then get way down the track to find we've got to implement expensive detailing on our non-structural elements to get the performance we need. And overall, we haven't necessarily found the most cost-effective solution. I'm really advocating for holistic consideration from the start of the project. Other things to be considered in this with the design for the structural is often we can be looking at lightweight roofs, which in standard, it's good value to have your cold form purlins supported on optimized steel rafters and portal frames. However, it needs to be discussed with the building services team if there are going to be plant and equipment that are going to be suspended from the roof or perhaps loaded onto the roof. And if it is, what are the gravity loads and seismic loads that the roof is going to need to resist? We don't want to get into a situation where down the track, they then need to install secondary structure, which often we find, if that's the case, end up again costing more money and potentially not just budget overruns, but program overruns. Also to be looking at the floor system. And does the floor system have sufficient capacity to look at those localized hold down for a plant and mechanical and electrical plant? And also just to be thinking about, if you've got larger sized filled water pipes, they've got considerable weight. And where is those components going to be resisted to, and where's the restraint going to come from? And just to think through those and collaboratively thinking about it so that the solutions are being chosen and thought about during the design. Also briefly, just want to talk about consideration of the post-earthquake performance. This isn't just to be considered when you're doing post-earthquake inspections, but when you're doing the design, to be thinking about in an event that's not a ULS event, what do I want my post-earthquake performance to look like? Just to note that structural damage can materially reduce the stiffness of structures. Reduced stiffness equals increased drift. So we need to be thinking about, are the drift-sensitive non-structural elements going to be more vulnerable to damage in future earthquakes? And then thinking about the repair methodology for the primary structure, that must consider the future seismic performance of the non-structural elements, not just the structural performance of the primary structure to achieve life safety. I also want to briefly just talk about residual drift, where residual drift of the primary structure can actually cause or present some unique challenges for restoring the earthquake damaged buildings. Here I've got a window which you can see, and you probably can't see, but there's a 0.5% drift on this particular building, and it's meant that there's a gap between the frame and the window, so this air can come into that particular room. But not only that, the actual frame has been damaged, and there's water ingress, so there's water tightness issues. Not only that, there was damage to the plastic cladding, so that replacement of the cladding in the window system needed to be undertaken. However, because the building's got a 0.5% drift, if you tried to install new windows into the window frame, which has now got 0.5% drift, you're likely going to get the same issue where your windows are going to have gaps, and you're potentially going to damage your windows by putting them in the first place. Of course, the perhaps suggested option would be to install the windows and the new cladding and new partitions vertical. However, you just got to be mindful that at the moment it's sitting at 0.5% drift. And if the building moves the other way to 0.5% drift, if the non-structural elements had been in their original form, they would have only seen 0.5% drift in the other direction. However, these new components that are being put in would have been seeing 1% drift, which makes these components significantly more vulnerable to damage in future events. So I just want to go into a section on what can be done to improve the seismic performance of non-structural elements. So as I've mentioned, I really want to highlight the holistic building design and coordination. That's all of the design disciplines, and that following through into the construction phase. That the primary structure is designed to achieve the seismic performance of the non-structural elements, in particular the drift sensitive non-structural elements, your partitions, firewall, cladding systems. That in some cases you're going to have design build for non-structural elements, and that's fine. However, the design team must work together to solve the challenges during the design phase to make sure there's sufficient room within the context of the building for the final design and coordination of the components by the contractor during the construction phase. Also, I want to just put it out there as an option is to potentially consider modularization. Can the in-ceiling services be modularized and constructed off-site with structural support frames, such that the completed sections can be brought to site and fixed to the building? I recommend one entity is given the responsibility for the installation and on-site coordination. So they're not doing all the installation, but they've got the responsibility for the on-site coordination of all the non-structural elements, including particularly those that are in the ceiling void. You've got your ceiling hangers, your building services, and your seismic restraints for all of those, including any restraints for your partitions. You want to ensure that the sufficient coordination has been done in the design phase, and when the contractor comes through and does their overlay for any design build components, such that if the contractor provides or suggests product substitutions, that they can be well considered before approval is given. So I'm aware of many instances where it appears that a significant saving is available. However, the knock-on effects are not well known, such that you actually end up with budget and program overruns for an approval for a particular product substitution, which, because there wasn't sufficient coordination done, it wasn't foreseen that was going to be an issue. And last, but as I say, definitely not least, independent inspection and QA sign-off. And if we can get that to confirm that the installation is not only code compliant, but actually meets the performance expectations for the project. just got a few more slides here just to highlight some areas, specific areas for consideration during the design. So choose an appropriate ceiling void depth. Don't skimp, because if you have too small a ceiling void, it can make the restraint services installation and the restraint installation complex and challenging. However, just want to highlight, be very wary of large ceiling voids because they have their own complexities and difficulties. When using metal deck concrete floor slabs, just be aware how many partitions have you got, how many firewalls have you got, because the trapezoidal profile you can see on the left there can actually be really challenging and expensive for the contractor to try and connect to and seal firewalls to. And potentially, if you've got lots of partitions, having a flat soffit profile deck may be a good alternative. You want to ensure you're using seismically qualified post-installed anchors, and just to be mindful that there are a number of anchors that have limitations on their use in the soffit of metal deck concrete floors. You want to specify and use seismically rated acoustic vibration mounts for plant. This is something which, the next one, thermal expansion of heating pipes, hot water pipes, steam pipes, and chilled water pipes. Need to make sure that any seismic restraints that are being designed and installed do not compromise the thermal expansion requirements. We don't want to be compromising the functionality which is going to be going on day in, day out by virtue of putting on seismic restraints. We want to ensure that hanging points for any that we're putting on are actually certified for the restraint loads that are expected. And just to note there that, bolted sheet metal ducts are often fabricated from very thin sheet metal. You want to be coordinating fire dampers and firewalls. So those are the penetrations through your partitions with the fire engineers and the building services team, and potentially the architect as well. Now, fire dampers are installed in the wall, and the ducts or whatever that's going through is hung from the slab above. And you need to just make sure that there's a compatibility of the movement between the duct and the partition wall drift to make sure that the duct does not prevent any breakup. And also, to make sure that any restraints that you put in adjacent to the breakaway joint doesn't actually stop the breakaway joint from actually doing its job in a fire and breaking away. You want to have appropriate flexible connections on mechanical plant and use flexible sprinkler droppers. And the last point there, you want to coordinate with a fire engineer for passive fire elements, and also you want to be talking to the architects as well. So currently there's a lack of testing to validate the post-earthquake performance of a lot of passive fire systems. Just want to note that some fire stop systems inherently have good fire stop performance in a seismic event because they're already seismically isolated or restrained as part of normal design. But just please, if you're doing any work in this space, please make sure you coordinate really well with the fire engineer and architect. So just moving into the conclusion, really just want to highlight that holistic building design. So I'm not advocating for a checklist. If you do these 5 things, you're going to do great. Every project is specific. Every project's different. You need to take each project on its merits and holistically think about the functionality, what's in the building, and work closely with all design disciplines, and then that coordination to follow through to the main contractor and subcontractor. And if we can get that, we're going to have a significant impact on improving the seismic performance of non-structural elements. So just very finally, improving the seismic performance of non-structural elements is going to reduce the need to close buildings following earthquakes and to close them to enable the repairs to be completed. We're going to improve the resilience and well-being of our organisations and entities occupying the buildings and residents of apartment buildings. We're going to be able to reduce the amount of waste generated to restore the buildings. And as a consequence of that, we're going to reduce our whole of life and body carbon emissions for our buildings. So thank you very much. I will now pass over to Jitendra.
Thank you, Jan, for your wonderful presentation. Now I'm going to talk about low damage details of drift-sensitive non-structural elements, which has been a part of my PhD at University of Canterbury. So first of all, a little about non-structural elements. They can be classified into extrusion-sensitive elements and drift-sensitive elements. Extrusion-sensitive elements are connected to the floors, and the drift-sensitive elements are connected to, they span from floor to floor such that they are subjected to the inter-story drifts. And the particular focus of this presentation would be on the precast cladding panels and internal partition walls. And in recent earthquakes, we have observed damage to these elements. So first of all, the general connection details for the precast cladding panels. They are attached to the structure. They are attached, They are attached to the structure either using horizontal slots or ductile rods. And the bottom connections are fixed or welded to the structure such that the relative displacements between the panel and the structure are taken by the sliding of the slots, bolts in the slots, and the flexing of the ductile rods. Another important aspect of these panels, it is the joint between them, which is generally interposed by sealant. And in these traditional systems, we do have a large corner gap between panels, such that the collision between the panels meeting at a building edge are avoided. Similarly, there have been a lot of literature and research recommendation around walls, partition walls, having vertical joints between the vertical structure elements or return walls, and allowing the wall to slide slide with respect to the floor above, such that the interaction between the wall and the structure is avoided till the gaps are engaged. And Mulligan and others have tested some walls with these gaps being distributed along the wall. So you can observe in these walls that the inter-story drift capacity is directly proportional to the vertical joint gap width. So if we require a high drift capacity, then we would also require a larger joint gap. So potential consequences of the damage would be economic loss due to repairs, interruption, and downtime, and there can be a life safety hazard due to collapse of heavy panels. So for my PhD, there were two main research questions. One was regarding the precast cladding panels to ensure a low damage performance while reducing the vertical joint gap between the panels at the corner to make it aesthetically better. And also in regards to the internal partition walls, the research was around providing a minimal vertical joint gap between the wall and the boundary elements, and also providing a low damage seismic performance. So first of all, I would like to talk about the precast cladding panels. So this was a detail we came up with during my PhD research. You can see on the left here that there is there's a panel with four steel embeds with vertical slots, where you can see a bolt in the slot which slides in here, and this slot is filled with grease to allow less friction to be developed. And these bolts are connected to the structure, having angles connected to them with horizontal slot to provide some tolerance. And we can add shims to provide outer plane tolerance as well. And the vertical tolerance is also provided by adding some packers underneath the panel. So you can also see here that there are weld plates which are also cast in the panels, so they resist the gravity loads from the panels. So during an earthquake or a lateral drift, we expect the panel to rock about one of the weld plates. And then the drift capacity will be given by simple ratio of the available slot divided by the lever arm. And also we can design the joint width between the panels based on the sealant properties and the geometry of the panels. So the first test we conducted was on a pair of panels which were placed on one side of the structure, which is in line with the direction of the loading. We applied a quasi-static cyclic loading up to 4% drift, and you can see here that the panels are rocking. The only damage that was observed was the tear in the sealant. So this was, let me just remove this. Yeah, so this one is classified as damage state 1 with slight tear in the sealant occurring at 2% drift. And this is damage state 2 where the entire sealant length was torn at 2.70% drift. So you can see here that there is some frictional resistance occurring between the bolt and the slot, but there was no visible damage to the panels and their connection. And the other test was on pair of panels. Here you can see there are 3 pairs of panels which are in line with the loading direction and in a certain angle. And there was one here at the back at the right angle. So you can see the panels are rocking. And we also tested 2x2 grid panels by introducing a secondary beam at the center of at the mid height of the columns to look at or to investigate the joints, the horizontal joints and the vertical joints. These panels also proved to be seismically resilient, but there were some issues which were observed, such as rotation of the nut during the rocking motion of the panels. But this could be solved by introducing a lock nut. And we could also we also observed there was debonding, sealant debonding occurring at junctions of these panels, and you can see the growth of that sealant here. So the main findings were that the panels with the rocking connection could be were damage free till their design drift. They also avoid larger joint gap widths, and friction also develops there, but the initiation can be designed. Sealant are also less susceptible to tearing and debonding, and loosening of nuts were observed. So further future research recommendations would be to look at the effects of dynamic loads on these panels and to check the cost benefit analysis for the construction and installation, and also investigate their interaction with the non-structural elements. Now I'd like to move into the internal partition walls. The first test we did was on a typical traditional rigid timber framed wall, where all the studs and top and bottom plates were rigidly connected together in a Y-shaped plan, where you can observe the behavior of the junctions as well. So we subjected this wall to quasi-cyclic loading as well. You can see here that it failed under a brittle failure mode. So the first hairline crack was observed at the junctions at lower than 0.1% drift. And then the second damage state was the significant screw failures that occurred at the bottom and the top plates. And when you compare this behavior, this behavior with the partition walls that were that were tested by Mulligan and others in a similar configuration, having 22 millimeter of vertical joint gap, we can see that the first damage occurred at 0.67% drift. So we can observe that having some kind of seismic gaps or seismic gaps can avoid the premature damage to the walls. Some of the test was conducted on partition walls with slots in the head tracks to accommodate the in-plane interstory drifts, and having a flexure bracket to also accommodate the outer plane drift as well. So you can see here the flexibility of the flexure bracket. So we tested these walls in Y and T shape. So you can see here, this is a line representing the bolt connection, the anchor connection between the head track and the floor above. You can see the wall is staying straight, and then the roof is sliding. But the problem with these connections was that we observed some wrapping of the slots, which started at 0.16%, 1.06% drift. But this was kind of like concealed within the wall, and the test we conducted on the flexure bracket is shown here, and the wall remained intact till 4% drift, and They provided superior seismic resilience, but more research has to be done regarding the fire rating performance and acoustic performance of these walls. The other the innovative idea of rocking interpartition walls is described here. So in this one, we came up with a box studs with timber planks attached at the bottom and top to increase their bending strength. And these box studs are placed at the ends of the wall, and we have aluminum angles connected at the top and the bottom of the wall, such that the force from the roof is transferred to the stud to initiate the rocking motion. And this is the dorsal track, where we have two tracks, one inside the other. And the flanges of the internal track were made longer to assist with the placement of the plasterboard, and the vertical allowance, the gap here, accommodated the interstory drift. So the general simple interstory drift capacity was given by the ratio of the vertical allowance by the length of the wall. If we go with a plaster joint, which is rigid, but if we introduce a flexible joint in here, then the capacity will be given by the ratio of the gap by the wall section width. So you can see here there's a schematic diagram here with the allowance given the top, and you can see here the walls are rocking, and we tested like 3 walls in planar walls. These 2 walls have box studs at the ends, and they had a plastered joints, but in this one we had only standard studs with sealant joint. So the capacity, the drift, design drift that was evaluated for these walls was 0.72, but we observed the screw failures at 1% drift, and the additional drift was attributed to the slackness between the aluminum angles and the steel studs, whereas for the wall with standard stud and sealant joint, the capacity was evaluated to be larger than this, but we observed failure earlier. This was attributed to the bending of the stud because of its weak axis, because of its weak strength in the bending mode in its weak axis. And then we tested a Y-shaped wall having a box studs and sealant joints, which were would vary from 5 to 7 millimeters. And we had aluminum angles at the junctions. We had it here to avoid interaction between the return wall and the in-plane wall. And the design drift capacity of the planar wall was around 1.20%, but we observed sealant debonding and screw failures early on, which was because there was a premature yielding of the aluminum angle because it didn't have a sufficient strength to rock the wall. So basically this wall was sliding. However, if you look at the performance of these return walls which rocked, could observe that that damage occurred after 1% interstory drift. So the main findings of this research was that the seismic gaps avoid damage to the walls. The slotted and bracketed head tracks, they have higher seismic resilience. The rocking walls with the dorsal track and box end studs can accommodate the interstory drift of the design drift limit, and the multi-winged rocking wall specimen suffered from the premature yielding of the aluminum angle. So the future recommendations on the research would be to check the dynamic loads on these walls, possibly with aluminum angles replaced with steel angles, and to check the cost benefit of these systems, check the interaction with other non-structural elements, and look at the acoustics and the fire rating performance of these walls. So from these slides above, we can see that the partial walls do require to accommodate the displacement demands from the structure, and we cannot ignore that. So while implementing the low damage design, we need to have a coordination and communication between the other disciplines, because each of them have a different responsibility towards it. So if we can coordinate in regards to inputs, details, how we are going to accommodate the moments, And also timing is one of the important factors. So we need to, for example, in partition walls, we need to lock in the deflection heads early on, so you can detail the restraints and do a spatial coordination and clash detection between the seismic restraints and the other elements. One of the examples to show the accommodation of the drift can be with a figure like this. So we have services penetrating through a wall, but if you have a deflection head track here, which allows the sliding of the lower part of the wall with respect to the top part, then the services passing above the deflection head wouldn't require us to detail anything to accommodate the interstory movements. However, for the services that pass inside the walls, would require a detail to accommodate the moments. So I would like to thank all the funding partners during my PhD research, and thank you.
Thank you, Jitendra, and thank you, Jan. Thank you very much. For your very interesting presentation. So we have had two really, like complementary presentations. Jan talking about the importance of holistic considerations in looking at the issues on a project basis and looking at dealing each project on its merit and doing things the right way. And Jitendra introduced a few solutions around accommodating large drift demands in flexible buildings particularly, and how we can have our drift sensitive non-structural elements detailed and designed adequately to accommodate the seismic demand from the structure. So ladies and gentlemen, if you are not aware, actually there is a question and answer link where you can pose your questions, and if you can find some questions have already been asked that you would have like to ask, then you can vote them up so that comes to our attention, and we will pose them to the panelists. So first of all, I would like to start with one question which is posed to Jan. Jan, there's a question from Graham. What would be good ways to handle contractor-led changes that might lead to uncoordinated non-structural element solutions? So can you provide your views on that, please?
Yeah, for sure. So really it requires really good coordination. And so it depends to what level the design team have taken it to, and then what level the contractor has taken it to. And so in terms of, your BIM LOD sort of 300 or 200 potentially, which is for the seismic restraints, if the design team took it through to that far, and then the contractor will take it beyond that. And now the point being is that if that hasn't been done, then the question really needs to be put to the contractor and the project manager or the PQS before they go ahead and make that a potential product substitution and approve it, is to say, hold on a minute, we need to make sure that we understand what that actually means before we go ahead and make that saving. So yeah, it really comes down to, if it's not coordinated, I know that's your question, how do you go about it? The reality is the contractor needs to do the work sufficiently to understand the knock-on effects. Otherwise, really, you can find it in complex jobs. If it's relatively simple, it should be obvious, but in complex jobs, you really are running a very high risk of running into budget problems and program problems as the project progresses.
Yeah.
I would jump in with the next question. I think we'll also direct this at you, Jan, keep you in the hot seat. I might actually combine a little bit the question from Sam and from Kyle, because I think they're sort of touching on the same point, which is sort of to do with sort of scope and responsibilities. Obviously, as sort of consultants, as we get into this design stage, we're sort of pulling responsibilities and scope sort of forward into the traditional kind of design timeframe. But obviously, there's some things which like you've been touching on still kind of happen during construction or just in time. Any sort of suggestions for how to sort of define these scopes and responsibilities, because obviously on different projects it might be slightly different, and sort of to get some clarity around what contractors are tendering for and that sort of thing.
Yeah, that's right. It also as a structural engineer or an architect, even trying to work out the size and form of the building, how big do we need our ceiling void to be, without having some idea of what the plant and equipment and what's going to be sitting in the ceiling void, we're in a bit of a loss. And so there has to be, as you were just saying, Andrew, you can't stop the inappropriate procurement process by having everything specified necessarily at the design, and not allow the contractor to bring their own options to the table, which is where that design build component is highly valuable. But really, I think what needs to be done is for the building services teams to be able to say, it's going to be a range of X to Y. If we allow this much space for whatever, or in terms of a piece of equipment plant that we're trying to restrain, this much, here's your range. That, to me, that's the way to try and separate the scope, is to make sure there's sufficient for the design team to do the design up front, and horses for courses, depending on how complex the non-structural elements are, and is how much more information is needed up front. But yeah, in terms of being able to look at hangers, gravity hangers, they're often a contractor component, but you need to make sure there's sufficient space to put them in there, and they're not trying to hang things off. You may have seen some of the pictures I had in my presentation. I flicked past them, but there were some pretty poor examples of contractors not having enough space and hanging ceilings off trapezes that were having electrical ducting and all sorts of things. You don't want that situation, or running hangers through a cable tray because they had nowhere else to put it. Those are the situations we really need to avoid by having enough information up front. So it's about having those conversations about the project manager and clients understanding the risk of how they actually put those scopes of work out. And if they push too much down to the contractor, there's just a much higher risk during construction that there's going to be issues. Hopefully that answers the question.
Yeah, no, thanks, Jan. I think I definitely think the seismic the earthquakes have flushed out this issue, but it's also, I guess, made evident there's also issues around gravity, and that's just a kind of a flow-on effect, isn't it?
Yeah.
Rajesh, you want
to? I want to follow up on another question directed to Jitendra. Jitendra, you have a question on, while partition walls are primarily drift sensitive, they do also experience high acceleration, particularly on out-of-plane direction, right? So, and also when large elements are fixed to the partition walls. So in your testing, was there any consideration for this, or do you think that this is a future area to explore? What's your view on that?
Yeah, for my testing, the primary purpose was to verify the design of in the partition walls, the low damage design for the partition walls. This wasn't considered during my testing, but this is a future testing scope for the partition walls. I believe there will be a testing in China where these walls will be subjected to the acceleration demands, and yeah, possibly we'll see the results during the test.
Yeah. Yeah, in those tests that Jitendra mentioned about that we're going to do in China, we will be anchoring some contents to the partition walls, internal partition walls on some floors, and that table of the anchored equipment will have some additional mass posed on the partition wall. So hopefully that'll give us some idea of whether having mass attached to the partition walls during earthquakes are going to pose any significant challenge to this type of partition walls that Jitendra presented. So that's good. Yeah. Andrew, do you want to follow up with any other questions?
Maybe another one for Jitendra from Namir around the category. I guess maybe it's regarding which part category, or whether you have to design the external cladding for ULS or SLS. maybe just want to comment around what different considerations you need to take for those two limit states when you're looking at precast panels.
Yeah, for the precast panels, for the rocky panels, especially for the SLS, would be like having the weather tightness in the sealants. So we would like to prevent that during SLS moments. So that will be designed for the rocking panels. We could design that. And for the life safety, I believe we should prevent the collapse of the panels. So that ULS limit will apply to the vertical slots there. So we can design them to match the drift limit, or we can go beyond that if required.
Yeah.
Yeah,
I
I'll
would
just
like to
add to that. Excellent answer there, Jitendra. That again, coming back to that holistic design, what are these components doing? So that the cladding is there ultimately is a weather tightness barrier, and so thinking first, what is the function of this component, and letting that help you decide when you're trying to decide your SLS limits, and then your ULS is often more obvious. How is this going to be a life safety issue?
Yeah, I would like to follow up with one question. Probably both of you might have some opinion on, and maybe Andrew as well. So there's a question from Hugh Cowan. Do you see emerging demand for the holistic approach you are advocating? And are there examples of effective leadership on this? Are there gaps in the building regulatory framework, or is this a practice issue? Right, so very important question. Thanks, Hugh. Jen, would you like to have a crack at that first?
Yeah, we're certainly trying on a number of our projects. It's in terms of holistic design, it requires a different mentality from the entire design team. And what we've actually done on one large project is actually sit down architects, building services, structural, and we had Seismic as a separate component, and all sit together and had multiple workshops, and to actually go through and say, what is your documentation going to look like at this stage in the design, at that stage? When are we going to start to coordinate the non-structural elements? When are we going to get the gravity hangers in? And we actually had open conversations about, in the past, this has gone wrong at this point. How can we stop that? So we are in some ways, it's new, and it's new for all of us. When I say new, it's happening on projects, but it is relatively different way of working very collaboratively when we cannot get into a siloed mentality. And it can be hard when you get into the thick of trying to get delivery out the door. I'm not going to hide from that, but yeah, trying to keep those lines of communication open. As you say, effective leadership there, Hugh, is actually really important. It's about keeping everybody talking and keeping everybody on task of what are we trying to achieve.
Yeah. Andrew, would you like to add something on that?
Yeah, I think I completely agree with you, Jan, and I am also, I guess, a big advocate for that holistic approach which Jan is talking about. I think, I guess one thing I've sort of seen over the last 10 years of when I sort of first got involved with this was it was very much a we're kind of shouting from the rooftops at first to say you need to be looking after this stuff and paying attention to it, because we could just see after each earthquake, the same thing was just happening time and time again, but often quite difficult to get client buy-in to it. And what sort of happened, particularly over the last sort of 3 to 5 years, is that's really flipped, and that I think clients and councils and I guess just the wider public are, I think, unhappy with going through a small to moderate earthquake and having this level of damage. So there's an expectation that things need to get better, and I think that they have also had enough pain with this, I guess, seismic restraint being sort of pushed down the road and running into issues during construction, that they can see the merit in work being done early on. So there's definitely been a big shift in how the industry is responding to it, and obviously it's still maturing. I might just jump to another question there from James around 3D modeling. That's, I guess, also coming in and playing a role, and I think is one way that we can have some good success stories around this holistic approach. But it's a bit of a horses for courses that it won't always be appropriate to 3D model everything. On a small, simple project, it's not all that useful, but on really complex, highly congested areas, it is. So, yeah, I think regarding the building regulatory framework, I think what we need rather badly is some better guidance documents to really set some frameworks and some just some standards around what's done. I don't think we can expect actual standards to come out to enforce this, but I do think some guidance documents will be really good just to create some standardization across the industry.
Yeah.
So I'm supposed to be asking the questions and answering, but yeah.
Thanks, Andrew. Yeah. I would like to move on to another question, probably Jitendra, addressed to you, like from Bevan. With the seismic gaps for non-structural elements, especially cladding, how do you ensure elements return to original position?
Yeah, for the cladding panels, we do have the washers that are locked in at 4 locations. So they ensure that the panels actually come to the original position. They are kind of like locked, so they don't go under horizontal sliding. Yeah.
Just a follow-up question from Graham. Jitendra, like T and corner junctions are usually where the lining damage occurs. Did you have any special consideration to take, to account for that, or any to look at the effects of drift on partition junctions, especially?
Is it for the rocking one generally?
Yeah, T and corner junction. Yeah.
Yeah. If this one was for the rocking one, then we expected that the aluminum angle that we placed at the corners would actually lower the interaction, but that wasn't the case. But we did another test on L junctions where we removed the aluminum angle and had one aluminum angle at the other junction, and then we looked at its behavior. So having that aluminum angle actually reduced the damage as compared to not having that aluminum angle at the junction. So we did have a look at it. Yeah, but I think we might have a chat later on probably to discuss about this.
Yeah. Thanks. We have only a couple of minutes now, so probably we have to come to the end. But before we do that, actually, I would like to just get to a question from Chris Wallington on do SPONs offer any references or guidance on deformation capacity of typical non-structural elements, or are there any references? So this question actually best for me to answer as the president of SPONs. So SPONs, the main objective is not to actually impose references or sort of guidance, or not to come up with the guidelines as of now. But we want to facilitate practitioners and researchers communicate with each other and gather all available practices, guidelines, and reference documents in one place. So if you go to the SPONs website, you'll see we are still building it up, but you'll see a lot of information actually how things are done in different parts of the world, and ultimately in future there is a long-term target of if we can come up with a general guidance that is applicable throughout the world, like on non-structural elements, and different countries can build up on that to have some specific requirements that switch to their needs and their practice and their seismic hazard, their consideration of risk, etc. So as of now, there is no endorsed reference or guidance from SPONs, but we are facilitating sharing information between different parties. So I think any final thought, Andrew, from you?
No, I think we're not quite sure. I think at 1 o'clock it might wrap up automatically. We're not 100% sure there, are we? So there's a couple of questions hanging out there, but we might have to wrap it up now.
Yeah. So I think what we'll do is actually, because you can always, obviously, we'll share the speaker's email so that you can pass on any questions to the speakers, and we will try to come up with these unanswered questions, like maybe we can answer the questions if you direct that to the speakers through their email. So that will be a better idea, because we don't have time left now. We have to wrap it up. But we do know, you may know that actually there is the third webinar coming up in a couple of weeks. The information on that is will be shared to you by the executive officer in a few days. But otherwise, I hope like we can see you at the NZSEE conference in April in person, and before then in other webinars that are coming up. So before I sign off, I would like to once again thank very much to the two speakers for their really outstanding presentations, Jan Stanway and Jitendra Bhatta, and my co-convener Andrew Baird also for his excellent leadership through the organization. And in the background, Lauren, the executive officer of NZSEE. So on behalf of New Zealand Society for Earthquake Engineering, I would like to thank all of you for attending this. And hope to see you sometime soon somewhere. Thank you and goodbye.